Hello, and welcome to this second online session. Could you please give me a signal that you can hear me well?
We can hear you.
Oh, thanks. And hi, Philip. Hi, Christian, Neo, Christian, Yun. Thank you. How are you? Uh,
Good.
so just give me, you can either unmute yourself, just say hello so we can contact or send me a message.
Hello, Peter.
Hey, how are you? What's your name?
My name is Philip.
Philip. Okay, good to have you here in this class. Okay. So again, so please keep yourself muted, but that doesn't mean that you cannot talk. Of course, you can always talk. Just unmute yourself, talk to me, and then mute yourself again. So I'd like to have questions, comments, etc. And it's a kind of easier if you talk than the messages. Okay, so last week I discussed discrete distributions, and this time, hello.
So you can split out the numbers so they can see it, which, by the way, they can see all these numbers.
Somebody is
And
not.
then the commentary is the same for both. Yeah.
Okay. I just unmuted everybody. So let's get back to where we were. I'm going to discuss continuous distributions, which are kind of different than the discrete distributions in the sense that a continuous distribution has possible values in a continuum. Practically either from, it can spread from minus infinity to infinity, or it may have possible values just within a range. But the point is that this is a whole continuous set, not just discrete points. Now, for a continuous distribution, the probability of a single number is zero. So if a random variable follows continuous distribution, then it's practically impossible to guess exactly what that random variable will be. And that's pretty reasonable because actually, think about it, you are guessing infinitely many decimals after the decimal point, and that's just impossible. What you can, of course, guess with positive probability is ranges or intervals. For example, you might be able to guess what's the probability that a random variable will be between, say, -1 and +1, or so on. Now, we have a way of showing a discrete distribution just by listing the possible values and the probabilities. Now, this will fare miserably for a continuous distribution because, first of all, there's an entire continuum of possible values, so you can't list those values. And secondly, and more importantly, all the probabilities are zero. So that sort of list wouldn't give us any information. So the way statisticians overcome this problem is showing something called the probability density function. So I drew one example here. I hope you can see it on the screen. So this is a so-called bimodal density function. You can think about it as a density function of a mixed population, say, results in a marathon run of professional and amateur athletes. So you can see there are two peaks here, one for the professionals, one for the amateurs. So now how do we use this density function? Well, the way to use a density function is this. Suppose I want to know the probability that the random variable having this particular distribution will be between -3 and +1. That probability is represented and illustrated by the area under the density function from -3 to +1. You can see the shaded area here. Of course, there are all kinds of shapes for probability density functions. Maybe one common thing is that the area under the density function all the way from, say, minus infinity to plus infinity has to be 1 or 100%, because that represents that the random variables between minus infinity and plus infinity. Well, a very central distribution for statisticians and probabilists is the so-called standard normal distribution. And you probably saw it already. Here is a way to create the graph of this density function. I wrote a little program in R. I'm going to copy-paste into R, although I have it in these notes already. So let's copy this. And I go to RStudio. And let's paste this up here. So I pasted it, and let's just run this little program. So basically this will show a bunch of numbers, 1,000 of numbers on the horizontal axis, and on the vertical axis it will show the value of the normal density function, of the standard normal density function above each value. You see there are two parameters listed here. One is the mean and the other is the standard deviation. The mean is now, I set the mean as 0 and I set the standard deviation as 1. That's what makes it standard normal. So if there are different other means or other standard deviations, that will be just normal without standard normal. Okay, and let's click run. And there you see it appears the standard normal distribution. This has this particular shape, looks like a mound, and it's symmetric. It's actually symmetric around 0, which is the mean in this case. That's how I selected it. Let's go back to the lecture. I'm showing the graph here as well within the lecture. And the graph below illustrates the probability that a standard normal random variable will be between minus 1.8 and plus, that's, I guess, what number? Minus 1.8 and 0.8. This line is a little bit off, so it's not very clear whether this is 0.8 or 0.7, but it should be 0.8. And this should be minus 1.8. So that this is the area showing in the red, that represents that probability. So again, what makes this normal distribution standard is that the mean is 0 and the standard deviation is 1. So if the mean is 0, that means there is a symmetry around, you can see, you can see there's a symmetry around the mean, which is 0 now. The standard deviation determines how fat this distribution function will be. Here are some properties of the normal distribution. So as I said, it's symmetric around the mean. There are two parameters, the mean, which is denoted by the Greek letter mu, which we are already familiar with, and the standard deviation denoted by sigma. And just like any continuous distribution, the probability of a single point is 0. And the function spreads from minus infinity to plus infinity. Notice that I didn't draw it from minus infinity to plus infinity, first of all, because it's not possible to draw infinity. I drew it from minus 3 to plus 3. So actually, even though there is a positive area beyond plus 3 or below minus 3, those areas are so tiny that we can safely disregard it on a practical standpoint. So I didn't draw it. You can see that it's close to 0. Mathematically, it never touches, this curve never touches the horizontal axis. But on a practical level, minus 3 to plus 3 is basically enough for us. Okay, now, there could be a standard normal density with mean 0 but standard deviation 5. Here's the same R program, the only thing I change is that SD equals 5 instead of 1. And the D norm function will return the normal density function value for every possible value of x. I will not copy paste this because I have this curve here in the notes. It looks very similar to the standard normal, not different. Really what changes is the fatness, which is showing in the labels of the horizontal axis. So instead of going from -3 to +3, it goes from -15 to +15. Why -15 and +15? Because the sigma is 3 now. So it spreads from -3 sigma to +3 sigma around 0. Beyond that, the area under the curve is very small, beyond the -3 sigma or the +3 sigma. And then I changed the mu to 10, so the mean will be now 10, and I kept the standard deviation as 5. And here is the curve. So now the axis will be 10, so this is the symmetry. And it spreads from 10 -15, which is -5, to 10 +15, which is +25. Okay, let's calculate a couple of things, a couple of probabilities associated first with the standard normal random variable. So calculate, here I have a couple of examples. The first one, probability that z is bigger than 0. Z will always stand for standard normal random variable, so when you see the z here, you know that it's standard normal, but I point it out anyway. Okay, so you don't have to do anything for this. You know that this is 50% because of the symmetry of the standard normal density function around 0. Okay, let's see the probability that z is between 0 and 1. Now, here we have to use R. Of course, this is a simple thing to look up. You can use any other software, but I'm using R for consistency because we already have R. I mean, you already took a course, etc. So let's use R. But obviously, if you wanted to use Excel for this simple lookup, it's fine. So the thing is that most of the software can look up probability that z less than a particular number, not that z is between two numbers. So, but that's enough for us. So first I'm going to look up the probability that z is less than 1. Okay? Here is a command, pnorm, that will show you the area to the left of the number 1. I show you how that works in R. I will not do this every time, but just show you once. So here I copy paste the pnorm. So 1 is the number. I want to know that the area to the left of 1, and I give the mean and the standard deviation. These are the default values, by the way. So I do that and hit run, and you got 0.84 rounded. You can see it here at the bottom. Okay, so let's go back to the lecture. So you got 0.84, which I copied here now. But that's the probability that z is less than 1. However, I only wanted to know the probability that z is between 0 and 1. So you have to subtract the probability that z is less than 0. But that's 0.5 by the symmetry. So the result will be 0.84 minus the 0.5, which is 0.34. My next example is calculate the probability that z is between -1 and +1. Well, again, we don't have to do any work for this because I already know the probability that z is between 0 and 1. Now, this area consists of two portions, z between 0 and 1 and z between -1 and 0. But the two portions by the symmetry are exactly the same, have the same areas. So I can just take twice the probability that z is between 0 and 1. So that gives me 0.68. Is everything clear so far? Please tell me if it's not. Thanks, Eric. Anybody else pitching in? Yeah, clear, good. Just give me a sign if there are any questions or any ambiguities. Tell me, because this is a very important part. You really have to understand the normal distribution. So I just want to make 100% sure that everybody understands. So no questions left. So if you have any questions, please feel free to ask and send me a message. Okay, I really want everybody to be clear with the normal distribution. It's very important for us. Okay, so let's look up probability z between -2 and +2. Well, that will not be very different from looking up the z between -1 and +1, except instead of the 1, everywhere you type 2, obviously. So I'm not going to go through this. What you end up with is 0.95. And my last one, p between -3 and +3. Probability that z is between -3 and +3. Again, we do the same thing as before. What we got is about 0.99. So you can recognize these probabilities if you remember the empirical rule. 0.98 for 1 standard deviation, 0.95 for 2 standard deviations, 0.99 for 3 standard deviations. And indeed, these numbers come from the normal distribution. These numbers are exactly correct for the normal distribution. So, and that's the origin of the empirical rule. Here I have another example just to make sure that everybody follows this. If it's not clear, tell me. I can also show it on an illustration on the iPad. So I can draw the picture, and that could make it easier. But I don't want to do it if everybody is clear on it, because I don't want to waste time. So that's why I'm asking. If it's not clear, that you just tell me. Okay, so I can draw a picture for this, for example, the probability that z is between -1.2 and 2.1. So let me give I'm going to give the board to the iPad. Just a second. Now just give me 1 second for this. Screen share. Because now I don't see how I can. Well, that thing. I can't find now that button which would allow me to share the screen from the iPad. Okay. Strange. Okay, unfortunately I can't do a drawing now. Somehow the system doesn't allow me. Maybe here. Okay. More tools, maybe here. Ah. Okay, so can you still hear me? Now I think you can see the iPad. Can you hear me? Okay. So what I wanted to do is show a way to calculate this probability. Yeah. So let's say, where's the lecture now? Okay, never mind. So I wanted to show, I don't have the lecture now in front of me, so I might change the numbers, but it looks like this. Let's go back to okay, so here is the standard normal distribution. And suppose I wanted to find the probability that a standard normal random variable is between, say, -2 and +1. So I'm showing the -2 and the +1 there. So that will be an area, right? Between -2 and +1. But this area consists of two areas, basically, from 0 to +1 and from -2 to 0. I'm showing the other area. Now, so basically what I'm doing is summing up the two areas from 0 to +1 and from -2 to 0. Okay, and so that's what I'm doing here. Now let me try to get back to the original. I want to show my screen. Okay, just a second. Now I don't seem to be able to get the lecture. Okay, here it is. Okay, so how do we do that? So suppose in this case, I wanted to know the probability that the standard normal random variable is between -1.2 and +2.1. Well, so but really it's a little bit, I'm doing it a little bit differently. So maybe I go back to the iPad. So it will be the difference between the area of the left of 2.1 minus the area to the left of minus 1.2. So maybe I go back there and so it was minus 1.2 and 2.1. So let's just show you again. Okay, so here is the standard normal. Here is the, so let's just do the minus 1.2, and here is the 2.1. Okay, so what I do is first I calculate the area to the left of 2.1. Okay, see the shaded area to the left of 2.1? And now I subtract the area from this, whatever is to the left of minus 1.2, which are going to double shade. So now you see that the area from minus 1.2 to 2.1 is basically the difference of the area I shaded first minus the double shaded area. Is that clear now? Oh, okay, thank you. So let's take back. Okay, very good, thanks very much. So let's take this back. Okay. So that's what I'm doing here. Basically, I look up first the probability that z is less than 2.1. That's the usual p-norm function. And then I look up the probability that z is less than minus 1.2. That will be the double shaded area, right? I got another number in R. I'm not going to copy paste. This is the command. You can just copy paste yourself if you like. And then the area from minus 1.2 to 2.1 is 0.98 minus 0.11, which is 0.87. Okay. Now here, next we are going to get a little different type of question. It says, suppose z is a standard normal random variable. Find the value w so that z will be between minus w and plus w with 95% probability. Well, here's a solution to this. We already saw above that w equals 2 approximately satisfies this requirement. We remember here we saw that the probability that was actually not 2, 4.4, that z is between minus 2 and plus 2 is about 95% probability. So we know that the w equals 2 roughly satisfies this requirement. However, here we would like to have a more precise result because that's what statisticians use. I know that 2 would be a good rounded answer to this, like that would be an approximate answer to this question. So I want to find the exact number. So basically, if the area between minus w and plus w is 0.95, then the area from 0 to w has to be the half of 0.95, right? Because of the symmetry. So that's 0.475. And the area to the left of w then has to be the area between 0 and w and the total area to the left of 0, which is 0.475 plus 0.5. So that's 0.975. So you type in R the qnorm command, which will do the exact opposite of what the P norm did. Now I type in the probability, and the Q norm will return the W so that Z is less than W with that particular probability. So it gives you W equals 1.96 if you type this command into R. So this is indeed very close to 2, but this is the number statisticians use. It will come up in the future material. So I wonder if this was clear, or should I explain this a little more? Could you give me some feedback? Philip, clear, thanks. Anybody else? Yu Cheng, thanks. Okay, I get like 4 or 5 answers. Does that mean that everybody else is clear, or? Okay, so Christine, yeah, I could explain it again. So here it is. So I'm looking for now a W so that the Z will be between minus W and plus W with 95% probability. Now you can directly read this out from R. So what R can do is there's the Q norm command where you can write down the probability, and then the Q norm will return a number so that the area to the left of that number will be exactly equal to the probability given. Okay, so what I'm doing, I'm converting it to that sort of question. Okay, so that's what I'm doing here. So if the area between minus an unknown number and plus an unknown number is 0.95, then the area from 0 to that unknown number will be half of 0.95. And the area from minus infinity to that unknown number will be 0.5 plus 0.475, because, well, from minus infinity to 0, we have area 0.5. So altogether, that will be 0.975. So now I converted the original question to a type of question such that Z is less than a particular number is equal to a given number. So now I can use the Q norm command, type in the given probability here, the given area, the 0.975, and it will return to you the number, the W. So that's 1.96. Christine, is that clear now, or I can also draw it if necessary? Christine? Oh, you are asking how I do the Q norm? Or could you just unmute yourself and maybe explain your question in a bit more detail, because I would like to know which part of this you didn't get. Christine? Hello? Yeah, but I understand, Eric, but I just wanted to know which part. Like, is that a Q norm that is not clear, maybe? Or because that's a kind of long derivation, I just want to know. Christine, could you give me some help? Like, which part of this derivation you did not understand? Hello, Christine, are you there? I don't hear you. Wait, I'm going to unmute you. Oh, everyone is muted, so. Christine, are you able to?
Hi, are you able to hear me?
Yeah, I hear you now. I'm sorry, it was unmuted, but now I hear you. So could you talk?
Yeah, so I guess I was just wondering how W is calculated in that equation.
Oh, but
I
are you
was,
talking about the Q norm part here, or before?
I think before, I guess I'm having trouble visualizing it.
You know what? I draw a picture then. Okay. I do a. Oops. I wanna mute the iPad. Hold on. Okay. So let me draw a picture of this. Okay, so you're gonna see it now. So what we are looking for is here is the standard normal density function. I'm looking for this W, or it is the minus W, so that the area that I'm shading here is equal to 0.95. With me, Christine, so far?
Yes.
Okay, so now look at so you can't directly look this up in R because it just R doesn't do it. All R can do is to tell you an area. If you give a number or area, then it can tell you the number so that the area to the left of that number will be exactly equal to the probability you gave. Okay, so I'm converting this to that sort of thing, to that sort of question. So I'm doing it in two steps. Look at the double shaded area. See the double shaded area? That's gonna be 0.475. Why 0.475? Because it's half of, it should be half of 0.95. Are you with me?
Yes.
Yeah, so that's 0.475. Now I add the entire, I double shade this, everything. Dig. Everything. I add all the area to the left of 0. That is 0.5. So this area, but not only here, but everything together like this and this together, that's got to be 0.5. Okay, so if this is 0.475, then the total area to the left of W is 0.475 plus 0.5, which is 0.975. Is that correct?
Yes.
Yeah. So now I converted this to a question because now I know that this unknown, to the area to the left of this unknown number is 0.975. But this is the kind of question. Oops, I'm not. Let's go back to the. Just one second. I wanna take it back. I don't know. Now my whole thing. Hold on a second. There it is. So I wanna take this back. Okay. So now I converted it to this kind of question, like the probability z is less than an unknown number being equal to a known probability, 0.975, and R can directly answer this kind of question. That's why I did it. So the command is a qnorm. I put down the 0.975. I keep the mean and the standard deviation. And if you copy paste into R, R will return the 1.96. Is that clear now?
Yeah. Yeah, I think the graph helped.
Okay, great. So it's always when something is not clear with concerning the normal distribution or any of these calculations, it's a good idea to have the graph drawn yourself and just see it in front of you. Okay, but thanks for asking, Christine.
Thank you.
Here is another exercise, but I don't solve this. You can just do it yourself. Find a W that the Z is bigger than W is 0.6. You can do it yourself. I will also assign other exercises, of course, in addition for practice. All the exercises that I will assign just for practice for the test. But so you don't have to submit the solutions to the exercises. Okay, now, what about not standard normal, but still normal distributions? So it's entirely possible that a random variable follows normal distribution, but the mean is not 0 or the standard deviation is not 1. So in that case, it's not a standard normal distribution. But so here is an example, a W, I don't call it Z now, and suppose you observe it as 185 pounds, and you know that W follows normal distribution, but not standard normal. Well, how do you interpret this information? If you know nothing else about the distribution, just that it's normal, you have no idea of the mean and you have no idea of the standard deviation, then this 185 gives you absolutely no information. Is it like shockingly large? Is it shockingly small? Is it kind of okay? We wouldn't know because there would be no comparison. So what we do is compare it to the mean and the standard deviations. If I know that the mean is 150 and the standard deviation is 25, then what I can do is convert this figure 185 to the number of standard deviations above or below the mean. So that will be calculated as 185 minus the mean divided by the standard deviation. That gives plus 1.4. So that means that this 185 is 1.4 standard deviations above the mean. So that shows that it's not a surprisingly large, not a surprisingly small number. We know that roughly 2 standard deviations away from the mean, that area covers about 95% of the total area. So being 1.4 standard deviations above the mean is nothing extraordinary. Okay, so in general, if X follows normal distribution with mean mu and standard deviation sigma, then you standardize this, you got X minus mu over sigma, I call that Z, and that follows standard normal distribution. So you can always make a normally distributed random variable into a standard normally distributed random variable just by doing this. So subtract the mean, divide by the standard deviation. What you get is a random variable with mean 0 and standard deviation 1. Here is another example for normal distribution. I'm spending a lot of time on this because it's pretty important. So suppose X is a normal random variable, but now it's not standard with mean 200 and standard deviation sigma. What's the probability that X will take a value greater than 228? Now here, again, remember, R can do for you the probability that X is less than a certain number. It cannot do a probability that X is bigger than a certain number. But that's fine because we can easily convert this to a probability that X is less than a certain number. In particular, the probability that X is bigger than 228 is 1 minus the probability that X is less than 228. So let's see. So what I'm going to type in R, P norm, 228, that comes from here. And then I type in the mean and the standard deviation. If you do that in R, you got the result 0.76. So that's the area to the left of 228. However, you need the area to the right of 228, so that will be 1 minus 0.76, which is rounded 0.24. Is that thinking clear now? Just give me a little feedback. Okay, thanks, Eric. Thanks. Thanks. Oh, thanks, Christine. I think we have two Christines here, so it's a little bit confusing. Let me see. We have. Okay. Okay, but thanks, Christine, for writing back. So it's clear to everybody. Okay, now here's another question, which comes from it's a more practical one, not just involving normal distribution, but an entire problem for business. So suppose that an automobile muffler is designed so that its lifetime is approximately normally distributed with mean 26.4 months and standard deviation 3.8 months. So the muffler is covered by warranty for 18 months. Question: approximately what proportion of the mufflers will fail within 18 months? So here's the solution. Let X be the lifetime of a randomly selected muffler. All I want to know is what's the probability that X is less than 18. So the P norm command will do that. Yes, so the P norm will do that. Let's see the work. Yeah, Mariana says it's different to watch it than to solve it on your own. Yeah, I agree with that, but just watch, and then there will be exercises, and those exercises will help you to do that. So you do the P norm, you copy paste from here, or you just type it into R, and you will get that 0.001. 0.01 is the result. So only 1% of the mufflers will fail within the warranty period. Pretty simple. Here's another one, maybe more complicated example, so watch this. A machine that dispenses cornflakes into packages provides amounts that are approximately normally distributed with mean weight 20 ounces and standard deviation 0.6 ounce. Suppose that the weights and measures law under which you must operate allows you to have only 5% of the packages under the weight stated on the package. What weight should you print on the package? So before we start with this, so what you produce has mean 20 ounces. And what should you write on the package so that only 5% of the packages are underweight? Do you think it would be less than 20 or more than 20? Just give me some guesses. Yeah, Philip says less than 20. Christian, less. Yeah, I think it's correct. Mike also says less. Mariana. So, yeah. So could you just give me a reason? Like, let's see, somebody who said less. Let's see, there is Mariana, for example. Why do you think that it should be less than 20? You can unmute yourself.
Yeah, can you hear me?
very well.
Okay, great. Hi, everyone. Well, just because if you definitely know that you're going to get fined if you state over, so better to state under.
Yeah.
And when you're solving for the unknown quality, so even on the first line, let W be the unknown quality, it would be the same way that we were solving in like 3 or 4 examples back. The shaded area would be less than the 20 ounces.
Perfect. Very well said, Mariana. Thank you. I want to emphasize the first point, what Mariana made very well, but thank you very much, that it should be less than 20 ounces, because even if you put down 20 ounces, 50% of the packages will be below 20 ounces. So you only want 5% of the packages, so surely it has to be less than 20 ounces what you put down on the packages. If you put down more than 20 ounces, you will get more than 50%, right? So that was Mariana's point. So here is let W be the unknown. Here's the solution now. Let W be the unknown quantity that gets printed on the packages. Our goal is that X less than W with 5% probability. Now this is already, now notice, we don't have to do anything with this, again, as Mariana pointed out, because this is already in the shape and form that R can handle. Okay, so I can just, okay, so I can just directly type in, use the QNorm command. I put down 0.05, then I put down the 20 and the 0.6. Okay, and what I get is 19.01, but obviously I'm going to round it to 19 ounces. Is that clear to everybody? How I get the 19 and why? Philip, thanks. Anubhav, thanks for responding. Okay, so it looks like people follow it. So nobody has questions, because I could also, draw this, but maybe we just. Okay, then if it's clear, then I just go further. Here's another important notation which comes up a lot, is the ZA. And you see the Z, and then you see an A in the corner in the lower left corner of A. The meaning of this number is that this is a number such that the area to the right of this number is exactly equals to A. So A will be a number. Maybe it's much easier. You probably don't understand this, but it's just too abstract. So let me show you an example and it will become clear. Let's find, so here is the illustration, but let's find Z 0.025. So A is a number. The A is now 0.025. Okay, so look at this. Yeah? Hello? So I want this area, which is blue here, I want it to be 0.025. And the number that is showing here is called Z 0.025. So whenever A is equal to 0.025. So I want to use the QNorm function, but I can't directly use it because the QNorm will give you a point so that the area to the left of that point will be a given number, not to the right. But that's okay, because I know what the area to the left will be. So if I want this A equals 0.025, then this area in blue will be 0.025. Then the area in white under the curve will be 0.975, 1 minus 0.025. So you use the 0.975 in the QNorm, not the 0.025. And you got back the 1.96, which we knew very well. I don't know if you remember, but that was exactly the number So the area between minus 1.96 and plus 1.96 is exactly 2. Is exactly 0.95, sorry. So if that is 0.95, that's another way of looking at it, then the area, the total areas to the left and to the right will be 0.05, so the blue area is again 0.025. Okay, so how is this calculation? Was that clear to everybody? Please give me some feedback. Okay, so no questions so far. Thanks, Mariana, and to everybody who gave a little feedback. So everybody's clear on this. I didn't hear from Christine. Christine, are you clear on this? Okay, great. Thanks, Christine. Good. I just want to make sure that everybody understands. Okay, now here's another example. Let's find z 0.05. So this will be a number, so that the area to the right of this number is 0.05. So then again, go back. If you want this to be 0.05, then the white area will be 0.95 because the total area is 1. So 1 minus 0.05 is 0.95. So let's go back. So basically the area is to the left is 0.95. So that's the probability. That's the area I'm going to use in the qnorm command. And you type this qnorm into R and you will get 1.64. Here's my last example for the z. A, find z 0.01. Well, actually I don't have the solution here. This will be just an exercise for you, but remember 1 minus 0.01. That's what you have to use in the qnorm. That's 0.99. Okay, and then you type in the qnorm 0.99. And you will get the z 0.01. So in this case, this blue area is 0.01, so the white area is 0.99, and that's the notation. So it is just to explain the frequently used notation in statistics, which is the z 0.025 or z 0.01 or z 0.05, etc. I want to get back to the binomial distribution and show you how central the normal is. I have more reasons for stating that the normal distribution is very central, but this is one of those. So the binomial distribution actually does look like the normal distribution, at least if n is large. First, I want to illustrate that it actually does not look like the normal distribution when n is small. So I select a small n, say n equals 5 and p equals 0.7. So what I'm going to show you is the entire binomial distribution when n is 5 and p equals 0.7. So it's 5 experiments, and the probability of success for each experiment is 0.7. And the random variable we are looking at is the number of successes in the 5 experiments. Obviously, that could have 6 possible values from 0 to 5. Here is a little program that I wrote to show the distribution, the full distribution. And I'm not going to run it because I have the picture here. And so all these lines above the possible value just simply show the probability of that value. And you can see that this really doesn't look like the normal distribution. I mean, it doesn't quite, I mean, it's completely different. It's clearly a discrete distribution. Now, if n is large, it's going to still be a discrete distribution, but it's going to look like the normal distribution in a way. So let's do that. So now I select a very large n, say 10,000. Now I am going to show from 6,900 to 7,100 all the possible values. I'm not showing all the 10,001 possible values because it's just too much, it's unnecessary. The probabilities for those will be very small. So here is the R command, which is not very important for us now. One thing you have to remember, if you copy paste from a PDF file, then you have to retype the quotation marks in R. So if you copy this over, just retype these two quotation marks around the H. So it's gonna do the plot, and the picture is right here. So look at this. It looks really like the normal distribution, even though it contains only of lines. So every possible value has a line erected above it, which corresponds to the probability. But the whole thing almost looks like a continuous curve eventually, and the shape is exactly like the normal distribution. You can also see that the numbers below 6,900 or above 7,100 are extremely tiny, so it was okay to ignore those numbers, although the possible values go up all the way to 10,000, but with very small probability at the edges. Okay, so you can calculate the mean and the standard deviation of the binomial distribution, and that will be the mean and the standard deviation of the normal distribution that is very similar to the binomial distribution. So the same mean, the same standard deviation. So it's not just any normal, you have to really fit that normal distribution on this binomial. So it should have the same mean, which is 7,000, and the same standard deviation, which I'm just calculating here using the formula for the standard deviation of the binomial. Then it's going to be 45.8. So here is an example. Suppose that you sell 179 washing machines, and with each sale you offer the buyer the opportunity to purchase an extended warranty. The probability that any individual will buy the extended warranty is 0.38. Find the probability that 70 or more customers will buy the extended warranty. So this is clearly a binomial distribution. You have 179 trials, and at each trial the probability of success, if I call success that the customer buys the warranty, is 0.38. So let X be the random number of them who purchase the extended warranty. So X is a binomial random variable. N equals 179 and P equals 0.38. We ask that probability that X is at least 70. We can use R to get this probability. Well, remember, with R we can also have probabilities that X is less than or equal to a certain number. So I take the probability that X is no more than 69 and then subtract it from 1. And you can do that in R. We already went through this last week. You will get, if you type in the 69 into the P binom, you will end up with 0.5924, and 1 minus 0.5924 is 0.4076. So this is the exact probability that 70 or more customers will buy the extended warranty. However, I can approximate this number just using the normal distribution. Remember, I have to approximate it with a normal distribution that has the same mean and the same standard deviation as the binomial. So I calculate the mean, that's 179 times 0.38, which is 68.02, and I calculate the standard deviation of the binomial, which is, you know, remember, n times p times 1 minus p, so that will give me 6.494. So now I'm using the normal distribution, and I want to calculate using now the normal distribution that x is at least 70. But there is a trick here. So the problem is that x is at least 70 or x is bigger than 69 is exactly the same for the binomial. Why? Because when we imagine the original question, at least 70 customers is the same thing as more than 69 customers, because there's no such thing as a half of a customer. However, for the normal distribution, it can take values between 69 and 70, like 69.5. So x bigger than 69 and x is at least 70 will give you different answers for the normal distribution. It gives you the same answer for the binomial. So we wouldn't know which one to use, the 69 or the 70 for the normal, because it's just a different way of phrasing it for the binomial, but it gives you different answers for the normal. So the way to do justice, we do the half. We go to 69.5. So in the normal, when we use the normal distribution, we use 69.5. Okay, so then I use the p-norm. I do 69.5 instead of 70, and I put down the mean, and I put down the standard deviation. I got 0.5901. But I wanted the probability that x is bigger, not that x is smaller. So I have to take 1 minus 0.5901, which is 0.4099. This is a very, very close approximation of the normal distribution. The 0.4099 is pretty close to the exact answer. That was 0.4076. The proportional error is just 0.56%. It's roughly 0.5% is the error. So you can see that the approximation is very close. Is that clear what we did with this approximation? Can you give me some feedback? Okay. Okay, good. Yeah, so the point is you can approximate the binomial distribution by the normal distribution, but you have to select, number one, you have to select the appropriate normal distribution where the mean and the standard deviation is matching the mean and the standard deviation of the binomial distribution. And the other thing is that you have to use the so-called continuity correction. The continuity correction is taking the half. So if I wanted the probability of at least 70, which is the same as bigger than 69, then in the normal, I'm going to take 69.5 to correct for this discrepancy that is caused by the fact that the binomial distribution is discrete and the normal distribution is continuous. Okay, I will skip this other example and let's go down to the very important subject, which is the distribution of the sample mean. It's actually also, this subject could also be entitled as the central limit theorem. So in order to introduce that, I have to talk to you a little bit about populations and samples. So suppose that you have a large population, say yearly incomes of all credit card holders from Citibank. Okay. Now, the population mean and the population standard deviation are denoted by mu and sigma. These are unknown quantities and they are called parameters. Why unknown? Because it's a very large population. We don't usually have it in the database. Okay, so we don't have an entire population in the database. So instead, what we do have is a random sample. Say we draw a random sample of size n equals 100. we can calculate the sample mean and the sample standard deviation, right? And these are known quantities because, you know, this is in the database. We have it in the computer, so we can just simply press a button and it will give us back the mean, the sample mean, and the sample standard deviation. The sample mean is denoted by the letter X bar, that's a symbol for it, and the sample standard deviation is denoted by S. Typically, we want to get information for the population mean mu based on the above two statistics. So these two are called statistics, the X bar and the S. And what we want to know is how, like we usually estimate the mu by X bar, and that's well known, right? You take a sample and then you calculate the sample mean and you think, oh, well, okay, the population mean is roughly estimated by the sample mean. I want to be a little bit more precise here. How good is this estimate? How good is the estimate of the population mean using the sample mean? Well, in order to answer that, what you have to know is the standard deviation of X bar. The standard deviation carries basically, it basically stands for the error. Okay, it's the average distance between X bar, which is the sample mean, and mu, which is the population mean. So what you do have to calculate is that you do have to know is the standard deviation of X bar. Now you may ask, how come X bar has a standard deviation? It's just a number. Well, not really. It's a random variable in the sense that before you draw the sample, you don't know what it is. The sample itself is random. So the sample mean is random. And as any random quantity, it has a mean and it has a standard deviation. Now, what is the mean of X bar? The mean of X bar is exactly equal to the population mean. So that just expresses the fact that it's a good idea to estimate the population mean by the sample mean. We don't make any bias. It also means that if we take many random samples and then average out all those sample means, so we get a grand mean, that will be very close to the population mean. So if the sample size is 100, but you take, say, 10,000 samples, each size 100, and average out the sample mean, you really get very close to the population mean. So that's the meaning of the statement that the expected value or the mean of the sample mean equals the population mean. It sounds a little bit like a tongue breaker, but it does have an actual meaning, which is outlined here. Okay, so this is the actual meaning of that statement. But more important is the standard deviation of X bar. So that's maybe not as obvious as the previous statement, but the standard deviation of X bar is equal to the population standard deviation divided by root of the sample size. This is a very important statement. It says that basically you get a much smaller standard deviation for the X bar if the sample size is bigger, because you see it's in the denominator, the square root of n. So it does make sense to have a bigger sample because the error that's carried in the sample mean gets smaller. Okay, so again, just remember this. Standard deviation of the sample mean is equal to sigma, the population standard deviation divided by root n. So this sigma of X bar is just a notation for the standard deviation of X bar, standard deviation of the sample mean. That's the population mean divided by root of n. But this is not just, this is part of the central limit theorem, but this is not the surprising part. The interesting part is this. Now, that's probably the most surprising theorem I have ever seen in mathematics. The central limit theorem says that X bar follows approximately normal distribution. The reason this is surprising, because I did not assume that the population has a normal distribution. So if you ever draw the histogram of a population, it's not necessarily, it doesn't have to follow normal. It doesn't have to follow normal distribution. Still, the X bar, the sample mean, will follow normal distribution. There's a really cute a website where this is illustrated, but now we don't have very much time, so I will skip this. But here is the web address that you can use if you want to look into this. Okay, so shortly, this is a shorthand notation for everything what I said. The X bar, this tilde stands for follows, N for normal distribution with parameters mu, this is the population mean, and sigma over root n, which gonna be the standard deviation of X bar. Now this is horribly theoretical, but let's look at an example and it will become much more clear. Suppose that you have a sample of 100 values from a population with mean 500 and standard deviation 80. What is the probability that the sample mean will be in the interval 490 and 510? Well, all you need to know is that the standard deviation of X bar will be not 80, that's the population standard deviation, but 80 over the root of 100. So that's actually 8. So X bar follows normal distribution with mean 500 and standard deviation 8. Not 80, but 8. So now we can calculate the probability that X bar is between 490 and 510 is a difference between two probabilities. The area to the left of 510 minus the area to the left of 490. And here is a little bit of program that you can do in R. If you copy paste this, you get 0.7887. Okay, so this we already know, this p-norm stuff. The new thing here is the important thing is that the standard that X bar follows normal distribution with mean, which is equal to the population mean, and standard deviation, which is the population standard deviation divided by root of n. Now, this rule is approximate, but it's a very good approximation whenever n is large enough. So it's not gonna n meaning the sample size. So the 100 is pretty large. Usually what statisticians, the cutoff point for large n is usually 30. So if n is bigger than 30, this law will hold all right. And I will have a little time to explain the concept of a confidence interval for a population mean. So what's a confidence interval is going to be an interval that we can calculate so that the unknown population mean will be in that interval with, say, 95% probability. An interval like that is called a 95% confidence interval. Christine says, is there a way to graph p-norm in R with the shading? Yes, I can do that. So for example, I guess what Christine has in mind is this, the 510 and the 490. So let me do it in R. Let me do it on the iPad. Just a second. Yeah. Okay, so here is the normal distribution, but this time the mean is 500. Okay, so this number here is 500. Okay, now I want to know the probability that it's between 510, between 490 and 510. So here is the 490 and here is the 510. And this is the 510. So I want this total area. So what I do want is this shaded area here, right, Christine? But R cannot give it to me directly. R can give me areas that are left of a given number. So let me show you this, like area like this. This area I'm showing to the left of 510. That would include the shaded area plus the other shaded area. Correct? I can look that up. That's what p-norm 510 will give me. And then there is the shaded area that are just shaded. Let's double shade this. So there's the double shaded area, okay, which is to the left of 490. It's here. And now you can quite well see that the shaded area I'm interested in is the difference of the two areas, to the left of 510 and to the left of 490. Right, so is that clear, Christine, now? So why I do the p-norm 510 and the p-norm 490 and then I subtract. Oh, great, thanks. There's another question from Yu Cheng. Why the question is asking the probability of the mean falls in the interval, not asking the probability of a sample value falls in the interval. Well, first of all, my answer is because that is the question, but that's a kind of ridiculous answer. But there's a reason that I'm asking that question, because it will lead up to the concept of a confidence interval. It's very important what's the probability that how far the x bar falls, how far is the x bar away from the mu, because that can be turned into a question, how far is the mu from the x bar, because these two are the same. And I do want to know, I know x bar, I don't know mu. So if I know x bar and I know, like, with a large probability, mu will be only this far from x bar, that gives me a lot of information, and I would like to know that. Okay, so and that's what actually we are doing. So let me. Okay, so, and we were doing exactly as a preparation for this. So if you want to do a confidence interval, that would be based on x bar. So I know x bar, and the confidence interval, again, as I explained, would be an interval so that the unknown population mean is in that interval with 95% probability. Well, the way to calculate this interval is exactly, now since we know the distribution of x bar, I take x bar as the middle point of the interval, so the left point will be x bar minus something, and the right hand point will be x bar plus something. And what is this something? Well, it's 1.96, which is the exact number. Remember, it would be 2 standard deviations. That's really the empirical rule. Like you take x bar plus minus 2 standard deviations, but instead of the 2, statisticians use the exact number, which is the 1.96, times the standard deviation of x bar, which is the sigma over root n. But the sigma over root n I already calculated it was 8,000 divided by square root of 200, which is 566. So this is a way to calculate a 95% confidence interval. It's x bar plus or minus sigma over root n. But there's a caveat here that this I cannot usually calculate. This was a little bit an artificial example because usually we don't know sigma. So what we do is we replace sigma by the sample standard deviation S. So here it is. If you do that, then you have to use a different distribution, which is called the t-distribution. However, there is not much difference numerically, at least if n is large, but still the t-distribution is used by statisticians. So if you substitute the sigma by s, then you have to use t alpha over 2 instead of z alpha over 2, or t 0.025. Remember here we had the 1.96, which is the z 0.025 for a 95% confidence interval. So here we have to use the t-distribution, which is pretty close to the normal distribution, at least if n is large. The df stands for the degree of freedom, which is n minus 1. And you see that the df, the degree of freedom, is 30. Then the yellow curve almost coincides with the dotted curve, which is the standard normal curve. If df is very small, say just 1, then of course it does not happen. But here is a formula for the confidence interval. Suppose that you want a 95% confidence interval, then there is a value called alpha, which is the complementary value to the 95%, which is 0.05, and you take alpha over 2. So that will be t alpha over 2, which is the number, so that under the t curve, the area will be to the right of that number will be alpha over 2. So basically everything is known here, except I didn't explain this t alpha over 2 very well, but here's an example. Suppose that the sample size is 20 and you want a 95% confidence interval for the population mean. Now I'm not assuming that we know sigma, so I use S, then I have to use the t-distribution. So then alpha will be 1 minus 0.95, which is 0.05, and alpha over 2 is 0.025. So we need to find t 0.025. To the left of t 0.025, the area will be 1 minus 0.025, which is 0.975. So this is the same logic what we used for the normal distribution, except now we use the t-distribution. But still I type qt instead of q norm and 0.975. So that's the area to the left of 0.025, and the degree of freedom will be n minus 1, which is the sample size minus 1, that's 19. If you type this into R, you got 2.09. Remember, the normal distribution would give you 1.96, so it's really not much bigger than what you get from the normal, but it is a little bit different. So what you have to use the t 0.025 here, you have to use 2.09. Okay, so I think I'm running out of time, so please read the rest of this PDF file. There will be another part which explains how to set up a confidence interval for a probability or a proportion. And unfortunately, I have to quit here. If you have any question, please feel free to email, and I can email back, or I can even talk to you in private and ask me about this stuff, because it's really, we're running out of time. So some part of this material you have to study on yourself. but I'm here to help. I wonder if there are still any quick questions for the end of this session. Question? Hello? Nobody has any questions? In that case, I would just thank you for your participation. I will assign the exercises in an email. And so thanks again and goodbye. See you next week.
Thank you.
Okay, goodbye.